Okay, so in this lesson, we're going to have a look at piecewise functions. But before we get there, I need to do this warm-up. It'll really help you if you graph these yourself. So have a go. We've got three functions here. We want you to graph them on just the same graph. So on your piece of paper, draw vertical and horizontal lines. Sort of helps if you've got graph paper. Really will, because you want to graph these accurately. Graph paper is really, really going to help you on this one. You want grid paper. So off you go. Graph those. Pause your video and graph them. Okay, so let's have a look at them. The one in green first. So we have here, f of x equals 2. There's no x's in it. That means it doesn't matter what your x value is, your y value is going to be 2. If your x was -9, y was 2. If your x was 0, your y would be 2. If your x was 5, your y would be 2. Join all those together and you get a horizontal line going through y equals 2. And for your blue one, this one's much more fun. Oh, what am I pressing on down there? Blue pen. Okay, g of x equals x cubed. So whatever your x value is, you cube it. Well, 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. Ooh, I'm going to go all the way up there. -1 cubed is -1. And -2 cubed is -8. So let's draw that in, and I've cheated because that's hard to draw on a big screen like this. And let's see if I can pick up the line I drew earlier. Yes, you see, it's horrible. It's very difficult for me to draw with the mouse. And what's wrong with my graph? Needs arrows. You know, I've got some arrows somewhere at the end of these. Come on, find my arrows. Oh, well, I thought I'd put arrows on. Never mind. Let's draw them by hand then. Oh, come on, blue pen. It goes down to -infinity and up to +infinity. And for your last graph there, this is an absolute value function, but look, it's a transformation. -2 on the inside the bars, that's going to send your absolute value function right to, and we all know, I hope, what the absolute value function looks like. It normally looks like that, but this is your reference point. It's going to move right to. It's normally at the origin. It's going to move right to, so it's going to be here. And then normally you go 1 to the left, 1 up, 2 to the left, 2 up. So from your reference point, 1 to the left, 1 up, 2 to the left, 2 up. From your reference point, 3 cross 3 up. And you can see the pattern. You're getting this line going that way. And when you go in the other direction, you normally go 1 to the left, 1 up, 2 to the left, 2 up. So we do the same. And you see this line going up there like that. And again, I have cheated. And here's one I prepared earlier. Somewhere. Find it. Oh, there's a bit more of it there. Okay, so there's our warm-up. Now, what we're going to do with that is we're going to turn it into this. Oh my goodness, what is that? It looks horrible. That was 3 separate functions. Can you see? We've got 3 separate functions, and we've got to turn them into just one function. That was f of x, g of x, and h of x, and we have to do something to this big hot mess. You can see these parts look sort of the same. They are the same as these parts after the equal sign, but we've only got one equal sign and one function. And then we've got all this stuff there, and I don't like the look of it, so I want to ignore it. That would be a very, very bad decision to make, because this stuff here is just about the most important part of the function, and we have to analyze and see what that looks like. This is a piecewise function. It's one function that its domain would be sort of given to you by this, and what this is telling us is the domain has been broken up into 3 pieces. For any x values less than -1, we're going to use this piece of the definition. For any x values between -1 and 1, we're going to use this piece of the definition. And if we have an x value that's sort of like 2, 3, 4, 10, a million, we're in this piece, and we have to use this definition. So we have to modify this graph. This graph is not acceptable. This is 3 separate functions, and we've got to turn it into one. So let's have a little look at what piecewise functions are. I keep on throwing that word at you, and you might not really know what it is. So let's have a look at what a piecewise function is. This is a piecewise defined function. Now remember the basic idea of a function. Functions, they assign one output to each input, okay? So you get one y value for every x value that goes in. And most functions, well, that's a lie, actually, in real life. This isn't true. But most of the functions that we deal with in math have got very simple rules. For instance, for every x, return x cubed. What do we mean by that? We mean we're looking at the function y equals x cubed. Whatever x is, our function returns, our y value will be that x value cubed. Or we could have it that every x returns this is still simple. Might not look as simple as that one, but still simple. For every x, return the absolute value of x minus 2. Those are simple functions. But some functions have more complicated and elaborate rules, and these are much closer to what we come across in real life. And I'm going to show you what I mean by that. So think about mailing. You've got a favorite uncle, and you're going to mail him a card for his birthday. But because he's your favorite uncle, you're actually going to put some gift cards in with that card. How much will it cost it to mail it? How much would it cost you to mail that? Now, they have a letter rate for mailing stuff, but if your letter gets too heavy, they have to start charging you more. So let's have a look at that in some more detail. So here's actually the real USPS mail rates for first-class letters. They have these special things for businesses where they buy their special franking machines, but that's not us. So any letter that's going to cost you 55 cents, as long as it only weighs up to 1 ounce. For every additional ounce, they're going to charge you another 15 cents. So let's think about this. If we sent our uncle this letter and it weighed, say, there's the weight in ounces along here, so only weighed about half an ounce. They're going to charge us, if that's $1, this is 50 cents, 55 cents must be about there. If it was a slightly bigger and heavier card, but it still didn't quite reach an ounce, it would still cost us 55 cents. If the card weighed nothing, well, we'd have nothing to send him. So, but as soon as it starts to weigh anything at all, it's going to cost us 55 cents. But if the weight was 0, we've got a hole in our function there. So anything up to, I've got hidden somewhere here, I've got a function, there we go. Anything up to and including 1 ounce is going to cost us 55 cents. What happens if we put a couple of gift cards in with that card and now it weighs more than an ounce? As soon as it goes over an ounce, we have to charge 15 cents more, which is going to be 55 plus 15 is 70 cents. So anything, as soon as we go over 1 ounce, it's going to cost us 70 cents. So 70, this point here, when the weight is 1 ounce, falls on the green part, but this red line starts at 1 ounce, but it just excludes that 1 ounce. Make it even heavier, we add on another 15 cents and be 85 cents. And that would be for anything that was as soon as you go over 2 ounces and up to 3 ounces. Okay, you're getting the idea? This is what we call a step function. Can you see it goes up in steps? It's actually a transformation of something called the greatest integer function. Your function holds one line until you go up by an integer. This is a transformation of that. And that's a real life example of what happens with a piecewise function. So let's go back to the one we had. Now, how can you tell this is a function? What's important about a function? Does it pass the vertical line test? If I take that vertical line, everywhere across, there's only 1 point on my function that's crossing that line. Remember, these are one function. It looks like 4 separate things there. It's not 4 separate functions. It's one function. And this must pass the vertical line test at no point. Must 2 points on that graph cross over that vertical line. So let's go back to this one. This is one function, and I'm missing a bit. Where's the bit I'm missing? Come on, appear. Appear from nowhere, please. Oh no, this was the hard bit to draw. Oh, it's gone. I'm going to have to draw it by hand. That's annoying. Okay, right, well, here we go. So for any x values less than -1, let's pick one. Let's pretend we had x's. You always start with piecewise function. You always start looking at these ugly bits over here, the intervals for which you decide which function you're going to use. If I had x is that's x is -5. -5 is definitely less than 1. It's definitely not between -1 and 1, and it's definitely not bigger than 1. It falls in this bit. So I'm going to use the definition y equals 2 for x is -5. And that'd be the same for x is -4, -3, -2. Or something special is happening at -1. Is that included or not? Yes, it's included. So up to that point, anything smaller than that, I'm using this piece of the definition. Now, we shouldn't really, go away. We shouldn't really put the y equals there. That kind of just helps me think about what I'm doing. So the next, if I took a value between -1 and 1, say 0, I would be on this part of the definition. Say I had x equals 0. I'm using this definition here, y equals x cubed. So 0 cubed is 0. I wish my graph was there. 1 cubed is 1. Do I include it or exclude it? Exclude it. That's the end of this piece. And it actually started at x is -1 excluded. -1 cubed is -1. So what I should have here is that little tiny piece of the cubic function. Remember, the cubic function went all the way down like that, but I've erased mine for some reason. Okay, and then we have to consider what happens as soon as our x values start getting bigger than 1. As soon as they start bigger than 1, I'm not in this part anymore. I'm in this part. And so I've got it dotted in to help me to draw it nicely. From x is greater than or equals to 1. Put in x is 1 in here. 1 minus 2 gives me -1, but I have to take the absolute value of that, which equals 1. Put in x is 1, absolute value of -1. So I'm filling in that hole there. So there is a 0.11 on my function. Then x is 2. 2 minus 2 is 0. Put in x is 3. 3 minus 2 is 1, and the absolute value of 1 is 1. And you can see I'm getting this part of the absolute value function that we drew in our warm-up. So if I leave it like this, does it pass the vertical line test? Well, the bits that I've drawn in solidly do, but all those dotted bits have to go. If you leave those on your graph is wrong. Get rid of them. That has to go. Get rid of it. That bit has to go. Now that's my graph of this function. If you need to draw in the other bits really lightly when you're constructing it, that's okay, but draw them in really lightly because you've got to get rid of them. If you leave them on your graph is wrong. It's disgusting. It won't do. Okay, so here's this graph. Here's one I prepared earlier. It's exactly the same one we've just been looking at. Let's discuss the domain and range and what this means for it. So the domain, as I go across my axis, starts with an arrow, goes across, looks like there's a hole there, but no, there's a point on the graph with that value. So I'm still got all these x values in my domain, still got them. Yeah, this goes all the way across to from positive infinity to negative infinity. I thought I had that pre-prepared, but I haven't, so I'll have to draw it in. Interval notation, please. Always interval notation when you're giving domains and range, please. And your range from the lowest value. Well, the lowest value looks like that point, which has got a y value of -1. Was it included or was it excluded? It was excluded, so exclude that. Then we go across. There's weird things happening, but every single y value I come across, there's somewhere on the graph that's got that y value, and it goes all the way up to infinity. So this one is going from -1 excluded. Do not put that on it or your graph would be, that would be wrong. Okay, I'm going to get rid of that because it looks a big mess on my screen. Don't want to look at that. Horrible. Okay, so let's have a look at this last question here. We're being asked for the function of 3. You can do this 2 different ways. You can use your graph to work it out. Okay, so this means when x is 3, what is the value of my graph? So go along. Where's my x is 3? Here. That gives me that point on the graph, which is the 0.31. But what would my answer to the question be? I want to know what f of x is. Remember, your f of x is your y? So your answer would be 1. Now, that's easy to read off the graph, but what happens if your graph is wrong? If you've graphed this incorrectly, then that answer is going to be wrong as well as your graph, and you're losing all your points. There is another way. Let's do it with algebra. Using algebra. Forget your graph, look here. Let's just do it looking here. And we are saying, what is my function of 3? So I'm thinking about when x is 3, my question is basically asking me, what does my y equal? I'm evaluating the function when x is 3. So how do I use this again? Don't look here first, look over here first and choose which interval x equals 3 fits in. 3 is not less than -1. Don't want that. 3 does not lie between -1 and 1. Don't want that. 3 is bigger than 1. I want this part. So I'm now going to calculate my function of 3. My y value is going to be the absolute value of 3 minus 2. I should put it over here, shouldn't I? Function of 3. Oh gosh, trying to write with my mouse. It's the absolute value of 3 minus 2, which is the absolute value of 1, which equals 1. See? I could have used that to check my graph is right. I could choose it, but it's much safer to do it algebraically. You might not want to, but it's a good way of checking your graph is right. Let's clear all this junk up there because it looks so ugly. Let's try another one. But a piecewise function is a function. It is a type of function, so check your graph passes a vertical line. Did I stress that enough on the last thing? Erase all those extra bits, please. If you draw those extra bits to draw it, get rid of them. Erase them before you say, this is my final answer. Okay, so goals for today. Learn to graph piecewise functions. I think we probably need a bit more practice on that. Review domain and range. We've done a bit of that. Review finding zeros. Review working with complex numbers. Shall we come back to those in a second? Let's do another piecewise graph. So, okay, ooh, there's the answer. Okay, let's have a look at this one. So you have a go doing this. Pause your video, and then we'll go over it. So pause your video now. 5, 4, 3, 2, 1. Here we go. Let's choose an x value. Well, let's look at what we've got here. Again, we've got a function. It's one function that's divided into 3 pieces. And these are the intervals we're looking at. This is saying for all x values less than -2. So for everything from this side going backwards, I'm graphing this. Now, there's 2 ways you could work this out. You could, if you want to, draw the entire graph of y equals -x squared, which is basically a parabola turned upside down, yeah? So it'd be there, there, there. 2 squared is 4, so I'm going down 4. 3 squared is 9, I'm going down 9. You could do that. You could do it that way. And that's the safest way to get the general idea of where it's going to go and then decide, but how much of this graph do I want? I don't want to include the vertex because look what this said. This said I just want to include the bits. So there was the whole graph. It went like that. Yeah. I just want the bit from here downwards. And do I want that point, yes or no? Is it included? No, it's excluded. So I'm going to start off with an open point there. And I'm filling in part of a parabola there, but it doesn't, I missed that point. It should have included that point. I'm trying to draw with my mouse. It's very difficult, you know. Do that, sort of. That almost fits now. Okay. It doesn't look like a parabola, does it? But we know that is actually part of a parabola. If we'd been asked for, if this had been up till +2, we would have had all of the parabola. We would have had, if this, let me draw this. If this hadn't said -2, if that had been +2, we would have used all the parabola from there to there. Yeah? Okay, but it didn't say that, so let's get rid of that bit I just drew there. Undo, undo. Yes, there we go. And undo that stuff I've put up at the top as well. Oh no, keep that bit, I like that bit. Okay, right, next part. So f of x equals -3. That's one of those easy ones. That's just going to be a straight line going through, horizontal line going through -3. How much of that line do we want? We only want the bits between x is -2 and x is 2. So from here to here, we want a line going through y is -3. So I want it to there. How does it end? This end is open. And this end is included. So this one is included, solid blob. Oh, you see, your graphing has to be really good. There's a gap between those two. There's a hole in our range at the moment. Let's see if this part fills it in. And the final interview. There was 3 parts to this piecewise function. Our final interval is of our domain. Our interval of domain is all x values from 2 to infinity. We're going to graph x minus 3 squared plus 1. Oh, let's think about this. That would be a happy parabola again. and its vertex is normally at 0, 0. It's been moved 3 to the right and up 1. So 3 to the right and up 1, that would be where the vertex was. Do I just want to the right of that? No, I want from all x values greater than or equal to 2. So the parabola would go through there, normally go 1 left, 1 up from your reference point, your vertex, 1 right, 1 up, 2 right, 4 up, because 2 squared is 4, 3 across, 3 squared is 9, yes. So there's my parabola, and it would keep on going. If I drew the whole parabola, it would have a point there and a point here, but I only want the points from x is 2. And if you want to double check that starting point, 2 take away 3 is -1. -1 squared is 1. 1 plus 1 is 2. So my first point should be at 2, 2. Yay, I got it right. Now draw in your parabola. Yay. Put an arrow on the end. Okay, there's our piecewise function. So our domain on that one. As we go across, x starts at -infinity from the left, crossing domain road, go from left to right, look left, look right. Far left is an arrow as you go across. There's no hole there. There's points on the graph somewhere that have an x value of -2. We have all those points are covered. There's a hole here, but there is a point on the graph with an x value of 2, so there's no hole in the domain. And it goes all the way across to infinity. So our domain is all real numbers. What about our range? Again, from range, you start from the bottom and you go up. Just once, even though it looks like there's 3 pieces, you don't scan up it 3 times and do 3 different ranges. No, you just do one range all the way from starting looking at -infinity up to +infinity if the graph goes that far. So the bottommost point is definitely an arrow, so it starts at -infinity and it goes up and up and up to -3. There are no points on this graph with a y value of like -3.9. Actually, that stopped at -4, didn't it? So it went up to -4. This point was open, so it was excluded. Then we had a gap. Now in your gaps, you can put a u if you want. That's optional. The next y value we come across is -3. And there's no points with a y value just smaller than -3 or bigger than -3. So that's just one single point. Even though it's open at this end, it's shut at this end, and all these points in the other bits exist. So we have that -3 on its own is included. Then we have a big gap. There's no points on the graph with y values between -3 and 1. So we have a gap, and that there is a point on the graph with a y value of 1. So that 1 is included, hard bracket please, and then your graph goes all the way up to infinity. Enough on domain and range, I think. Our function of -1, let's do it 2 ways again, because it's a good way of checking our graph. On our graph, this is saying when x equals -1, when x equals -1, the question is asking us, what does our y equal? What's the value of our function when our input's -1? Go to -1, no graph up here, my graph takes me to there. And my y value is -3. Check it algebraically. Go up here. Look in here first to decide which piece we want. If our x is -1, -1 is not less than -2, so I don't want that. -1 does lie between -2 and 2, so I'm looking at this definition, which hasn't even got an x in it. It's just saying if your x, whatever your x value is between there, your answer is -3. Yay, we got it right. Okay. Now, I'm going to publish the whole of the rest of this presentation, which has got all of the answers given in. So, and to be honest, I'm going to tell you the truth. This is your homework. We're doing your homework in class. What I might do in a second is do another little video for you for the other part of your homework, which was these bits. So let's pause this video and start a new video for you. Stop.